Today's lesson is 9.4, conditions for rectangles, rhombuses, and squares. So yesterday we learned about what properties rectangles, rhombuses, and squares share, but today we're focusing more on how can you prove that it actually is one of those shapes based off of some of those properties. So first one we're going to cover is how to show that a parallelogram is indeed a rectangle. Well, there's one of two ways you can do that. First of all, if you have currently a parallelogram, so you've already proven somehow that that's a parallelogram, whether you have opposite sides parallel or whatnot. You do already have that established. If that parallelogram has just one right angle, that is enough to prove that it's a rectangle. Why? Because in a parallelogram, your consecutive angles will always add up to be 180 degrees. So if that's 90 degrees, this must be 90 degrees, and therefore this one must be, and therefore this one must be. So that's why you only need one angle to be 90 degrees and a parallelogram. The parallelogram takes care of all those other 90-degree angles for you. So yep, all you need is just that one 90 degree in a parallelogram, therefore rectangle. The second way you can prove it's a rectangle is if your diagonals, remember those are the lines that are going from one vertex to the other all the way across, if those are congruent to each other, so same length, and it's a parallelogram, then you have a rectangle. So again, notice both of these are starting with, it first has to be established that it's a parallelogram. Always that first. Then you can have one more piece of information, such as one right angle or those congruent diagonals. Then you've got yourself your rectangle. Let's see, the diagonals, congruent. Definitely wanted to highlight that too. But again, both of them have to start by knowing a parallelogram. So using those, oh no, this information down here, can you determine whether this quadrilateral is necessarily a rectangle? Prove it's a rectangle and explain your reasoning. Well, let's see what's being provided. Number 4 says we have EF is congruent to GF. FG is congruent to HE, FG, HE, okay, and FH is congruent to GE. All right, so this diagonal is congruent to that diagonal. All right, these are the diagonals. All the other sides I already went ahead and marked. So, does this prove it's a rectangle? Well, first of all, do we have a parallelogram? I know we do have our congruent diagonals. Is this part of a parallelogram, though? Are the opposite sides also congruent and parallel? These two, they are. Ooh, F, G, H, E, making sure I did that right. And EF and G, oh, you know, I think that is a typo. It is. Oh, how about that? We just found that out. Okay, so EF should be congruent to, this should be GH. That's what we were going for. Whoops. Okay, that makes more sense now. So given opposite sides congruent and, okay, so opposite sides congruent, that is one way you can prove a parallelogram. So just by knowing those two pieces of information, we do have a parallelogram, right? And that's the first condition up here is if you have a parallelogram with one of these extra things. So do we have one of those extra things? Yes, the diagonals are congruent. So parallelogram with congruent diagonals, yes, that is a rectangle. And that is why. Parallelogram with congruent diagonals. Let's check the second one. This is having to do with the angles this time instead of the sides and the diagonals. FEG, from F to E to G. Okay, so this angle right here is 45 degrees, they are saying. All right. And GEH is 50 degrees. That one right there, they just said. Okay, 45 and 50 together, what does that make? Well, isn't that, wait, 45 plus 50? I'm so used to seeing a 90-degree angle there for rectangles, but that's not 90 degrees, is it? That is 95. This is your reason why it is not a rectangle. Rectangles must have all four corners 90 degrees, and this one does not. So let's say, no, angles must be, oops, 90 degrees. Yep, not 95. That doesn't work for a rectangle. So those are the types of problems that you should be ready to see. You'll see those on your homework to get you some more practice with those, as well as the next test or quiz. So that's how you can prove it's a rectangle. Now let's focus on the rhombus. How can you prove that an already established parallelogram is a rhombus, like all sides are the same, right? So here are 3 ways that you can prove a parallelogram is a rhombus. The first one, if only one pair of consecutive sides, so that means the 2 sides right next to each other. That's what consecutive is. So not across from each other, but next to. So one pair of consecutive sides of what's already a parallelogram, right? These all start with parallelogram first. Yep, you have opposite sides parallel, and then on top of that, you have one pair of congruent consecutive sides. Then, oh, yeah, are congruent. Then that is indeed a rhombus. Because those are running parallel and it's a parallelogram, opposite sides congruent, opposite sides congruent. That is why it works. So I'll erase those because we're only starting with those 2, but that is why that works. Opposite sides are congruent, and if those 2 sides are the same, the other 2 must be the same, and therefore a rhombus. That's one way you can prove it's a rhombus. A second way to do that is to start with, again, a parallelogram. That's what these all start as. You already have a parallelogram. This one, the diagonals, if those are crossing at a 90-degree angle, remember that is a property of a rhombus. So if you see that occurring within a parallelogram, then you better believe it, you've got a rhombus. So definitely look for those perpendicular diagonals. Definitely a rhombus. Maybe a square, but at least a rhombus. And way number 3 to prove it's a rhombus, if you have just one diagonal of what's already established as a parallelogram. All right, so we've got our parallel sides, and we only have one diagonal is splitting those angles. It's bisecting them. Bisecting a pair of opposite angles, just like that. It's splitting them into 2 equal angles. Then you've got a rhombus. So for example, maybe if this is 50 and this is 50 and opposite angles are equal, so that would be 50 and that would be 50. Yeah, if you see that going on with just one diagonal and it's already a parallelogram, you've got a rhombus, because that's true of all rhombus's angles. Opposite angles are always bisected. Now again, what do you notice about the beginning parts of each of these theorems? Specifically, each quadrilateral starts out as a what? Yeah, each one starts out as a parallelogram. All of these have to start out as you already know it's a parallelogram, and then what extra piece of information or what other property then proves it's a more specific type of parallelogram. For example, rectangles, rhombuses. Last one we have, oh, here we go. Let's write a 2-column prove. Prove that if one pair of consecutive sides of a parallelogram are congruent, here we go, like these 2, then it is indeed a rhombus. Okay, we can prove that. First of all, they need to tell me, yes, it is a parallelogram. We already have that established. Oh, and there's the extra 2 sides, those 2 marked in green. Yep, we have those 2 sides congruent. That is one of the reasons we listed, but we're going to actually prove why that's always true. Why does that always work? So remember, in your 2-column proof, what always goes first? The given information, right? So that's what I'm going to write first. First, that it is a parallelogram. We have parallelogram JKLM. And you can definitely just draw that shape there. That's fine. That means parallelogram. And what else was given? Those 2 consecutive sides were also given to us. Given. Okay. Prove it's a rhombus. Well, we already know that JM is congruent to KL. Why? Because if it's a parallelogram, then the opposite sides should be congruent, right? Same for the other 2, the left and the right side. KJ should also be congruent to LM for the same reason. So I'll put those both for step number 3. And then step number 4, we can actually end with, yes, it is indeed a rhombus, because we've already proven that all those sides are congruent to each other. So that will be the last step. And this highlighter has a mind of its own. Why? Because you could write definition of a rhombus, but what's more specific is that all sides are congruent. Therefore, rhombus, right? That's the main reason. And that's why that way always works. You just need a parallelogram with one pair of consecutive sides congruent. That's why it works, because opposite sides are congruent within a parallelogram. Now let's write a two-column proof that if the diagonals of a parallelogram are congruent, then the parallelogram is a rectangle. Okay, so this is one of the reasons we know, but we're actually proving why this always works. So if we already have a parallelogram with congruent diagonals, therefore it's a rectangle. But why does that work? That's what we're focusing on now. Givens always first is parallelogram, and diagonals congruent. Yeah. So those two are congruent to each other. So why does that make it necessarily a rectangle? Well, remember those rectangles must have right angles. They must have opposite sides congruent. The fact that it is a parallelogram, pretty sure you can just end that with EFGH is a rectangle, because if you have a parallelogram with congruent diagonals, that was one of the ways, right, that we can prove. Therefore, it is a rectangle. So EFGH is a parallelogram. Let's see, we got EG congruent to FH. Okay, we got our diagonals congruent. Which conclusion is incorrect? Okay, can we conclude that it's a rectangle? Do rectangles have congruent diagonals if it's already a parallelogram? Yes. That is one of the methods of proving a rectangle. Is it a square though? Well, do we have any information that tells me all the sides are congruent? Or I guess we have right angles with the rectangle, but no, we don't have enough information to prove that that's a square. Sides, not all congruent.